Hello everybody and welcome to my presentation, A Taxonomy of Anomalies in Log Data. Before I introduce our taxonomy for log data anomalies, I would like to briefly explain why log data anomalies are so important. Current IT infrastructure are very complex due to the large number of different services. Therefore, the IT operators of these systems need to support to cope with the complexity and to ensure stable IT operations. This is where AIOPS comes into play, IT operations supported by artificial intelligence. In order to quickly detect errors and irregularities in the systems, anomaly detection is a major field of research in the area of AIOPS. Anomaly detection can be performed on several data sources, such as metrics, traces, or log data. For our taxonomy, we will look at log data in this case, as it's one of our main sources for troubleshooting. As it is an important field of research, countless different anomaly detection methods have been explored in the last years. To name a few important ones, DeepLog, LogRobust, and LogSee are based on neural networks and have been proven good performances on different datasets. The methods listed here are not complete, of course, but they reflect the many efforts of the community. Since there is a large number of algorithms, it is difficult for the IT operators to find the right one. To do this, they need to know what kind of data and therefore what kind of anomalies the datasets may contain. Therefore, the question is, what kind of anomalies do I have? To answer this question and to find out what kind of anomalies we are dealing with, we have created a first anomaly taxonomy for log data. A general categorization of anomalies was made by Shandola et al. In 2009. They were divided into point and context anomalies. Point anomalies are described by the fact that individual points are either outliers, as shown in the left image, or by the fact that they do not lie within a certain value range, as shown in the right image. In contrast to that, the values of the context anomalies are in the normal range. In the example, the epsilon values do not differ, but the individual points are formed into an anomaly by their surrounding points. We see that the points in the anomaly do not follow the pattern of the others. If we transfer this knowledge to texts, we can determine the following for point anomalies. Either a whole sentence is an anomaly, or an individual word in a sentence is an anomaly. As shown in the example, on the left side, the whole sentence is an anomaly, and on the right side, only these two words pose the anomaly. In contrast to that, in the field of context anomalies, the following cases could be imagined. Either a sentence does not fit causally in the place as in the left example. Here the mail is sent before the mail server is started. Or as a second example, we have again a reoccurring pattern, like in the right example, which is then suddenly interrupted. Now we move on to the taxonomy. In order to apply the anomaly types to log messages, we first must clarify what log templates are. Log templates are used for many anomaly detection methods. The underlying structure is abstracted and the log messages are split into a static and a variable part. The static part is then the log template. Several log messages can have the same template. An example are the following two log lines, which are expressed by the template start, whatever, service, add node, whatever. The attributes, the variable part, are then mail and volley 001 for the first log message and printer and volley 005 for the second log message. Next, we need to define the term context in the context of log data. The context of a log line consists of the templates around it. We use the template instead of the log message to have less noise. Formally, the context is described by following equation. The example below shows the context for a log line with parameter a is 2 and b is 1. So the context is built from 2 log lines from the past and 1 log line from the future. The context itself then consists of 3 templates of exactly these log lines. Here we can examine our anomaly taxonomy. The log anomaly taxonomy is divided into point and context anomalies to keep in line with the general and well-known categorization of anomalies. The point anomalies are then further divided into template and attribute anomalies. This taxonomy is meant to be a first classification approach to distinguish between different types. Our calculation method I will present during the next slides to distinguish the anomaly types for each anomaly and then to categorize them according to the taxonomy into the 3 different types will then not make any final decision, but it will generate values between 0 and 1 and thus express how strongly a certain anomaly type is pronounced. Let's start with the calculation of the template anomaly. The template anomaly should express how strongly the anomaly depends on its own template. So the question should be answered if a certain template always leads to an anomaly, or can it be that this template can also be extracted from normal log lines. Therefore, all log lines with the same template share the same template anomaly score. The template anomaly score is 1 if the template occurs in connection with anomalies only and never in connection with normal log lines. The formula describes the score as the occurrences of this template in anomaly log messages divided by the occurrence of this template in all log messages. Next, I present the score for the attribute anomalies. Here we only consider whether the log line becomes abnormal due to its attributes. To calculate the score, we divide the count of an attribute in an abnormal log line by the number of this attribute in all log lines. Since a log line can have more than one attribute, the attribute anomaly score is expressed by the largest anomaly score for all attributes, as you can see in the equation. At last but not least, we compute the context anomaly score. The context anomaly score should indicate whether the anomaly can be identified by its context. The score is then calculated over the number of occurrences of this particular context for the current abnormal log line, divided by the number of occurrences of this context in the entire dataset. Since the scores each gave values between 0 and 1, we looked at the distribution of the different anomaly types for different thresholds at 3 different public available datasets, namely BGL, Thunderbird, and Spirit. As soon as the scores exceeded the threshold, we classified the anomaly score accordingly. It is interesting to note that the BGL dataset has no attribute anomalies at all, and the other datasets has also none once the threshold is high. The template anomaly is the most common anomaly at all in all datasets. Since there is no direct ground truth, as there is no categorization of anomaly types in log data so far, we have investigated in our evaluation how different methods can cope with the different anomaly types. For this, we evaluated 5 different anomaly detection methods: deep log, A2 log, PCA, invariance minor, and isolation forest. There, we investigated the effectiveness of those methods for the 3 different anomaly types according to our taxonomy. As mentioned before, the BGL dataset has no attribute anomalies at all. That is why they are not shown here. The evaluation was performed with a threshold of 0.7 for all anomaly scores. In general, neural network-based approaches such as deep log and A2 log performed better in all 3 anomaly categories. independent of the training and test split. It can also be seen that all methods have been more problems in detecting context anomalies instead of detecting point anomalies, such as attribute or template anomalies. Now I want to finish my talk with a small conclusion and some insights to further work. With this work, we have for the first time created a general classification of anomalies for log data. This allows IT administrators to get more and better insights into their data. It also allows them to compare multiple data sets and see if they contain the same type of anomalies. From this, better decisions can be made for the right anomaly detection method decisions. In further work, we want to make the taxonomy more detailed and also work out subtypes for context anomalies. Thank you very much.